Let's show a transformation of three variables. Let's say that x is some function of u v w, y is a function of u v w, and z is a function of u v w. The transformation structure will look like this. We're going to find another triple integral over the transform region of u v w, and this is going to be f of x of u v w, comma y of u v w, z of u v w, and then we have the good old-fashioned Jacobian, and we're going to write it as par x y z over par u v w. And then this will be dv, or I'll just write du, dv, dw. So the Jacobian, without the absolute value, is going to be par x, y, z over par u, v, w. Let's see if we can get this pattern down. Remember, it's going to be a determinant, but this time it's going to be a 3 by 3 determinant. So we'll do par x, par u, par x, par v, par x, par w. Next line would be par y, par u, par y, par v, par y, par w, and finally par z, par u, par z, par v, par z, par w. Nice. And I would assume at this point that you know how to do a 3 by 3 determinant. Now, the two specific transformations that we will make in this section are going to be the cylindrical, x is r cosine of theta, y equals r sine of theta, and z equals z. Now, we learned from the last section that it doesn't have to be this exact order. For instance, last section we had y as r cosine theta, z was r sine theta, and x was equal to x. But in any case, here we have x, y, and z in terms of r, theta, and z. And we will prove this, but you should know and memorize that the absolute value of the Jacobian for cylindrical coordinates is always r. Always, for r greater than or equal to 0. This is always the case. And our other transformation that we will make is the spherical coordinates. So x is going to be rho cosine of theta, sine phi. I had you memorize this in an earlier unit. Y is rho sine theta, sine phi. And lastly, z was equal to rho cosine of phi. Now, the absolute value of the Jacobian in this case will always, 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 always be rho squared sine phi. That is always the case, and I'm going to have you commit that to memory. We're going to prove it, but once you prove it, always know that this is true. I guess I should also point out that phi, as you remember from before, is always between 0 and pi. So we don't have to worry about that being negative at any point. Our first example comes from section 15.7, number 18. You're going to see that these are very similar to the ones we just did in the last section. So we're back to the first octant. That's all plus x plus y plus z. And then you have a paraboloid facing down. So that paraboloid is, again, only in the first octant, so it's going to look like this. Like before, I give a projection. In this case, I project onto the xy, and projected onto the xy, I have this quarter circle with a radius of 1. So I make my cylindrical transformation. I've got another triple integral, and I have to substitute these transformed values into the function. So a little bit of a pain, but r cosine of theta cubed plus r cosine of theta, that's my x, times y, which is r sine of theta. That got squared like that. Good. And then we need our Jacobian, or the absolute value of the Jacobian, which is r, and we'll go dz dr d theta. So theta then is going to be fixed from 0 to pi over 2. R is going to go from 0 to 1. And now z is going to go, like we talked about in the last unit, flat against this Cartesian plane is where we start. Z equals 0. And we finish by going up to the paraboloid at z equals 1 minus. Now you'll notice here we have x squared plus y squared. So 1 minus the quantity x squared plus y squared. So 1 minus r squared. And there we have our successful transformation. Next example, 15.7, number 20. We're going to make a transformation here. I'm going to look at the projection onto the Cartesian plane. We see we have cylinders, 2 different cylinders. One cylinder has a radius of 2. And this cylinder has rulings parallel to the z, so this tunnel is going to be coming out at you and back into the computer screen. The other cylinder is one with a radius of 3. Same deal, rulings parallel to the z. So this is what it looks like on the Cartesian plane. Now, on the bottom end of things, which is kind of nice, is just the z equals 0 plane. So that's flush against the Cartesian plane. That's where we start inside this region here. And then we start at that plane and we move up towards your eye until we hit this plane here. And so that should help us set up this integration. Okay, so I did the integrand where it said x, and I made my substitution here. Okay, now I can't forget my Jacobian at the end of this, and we'll go dz, dr, d theta. Okay, let's fix theta to be 0 to 2 pi. R is going to go from radius of 2 to radius of 3, and then z is going to go from the bottom plane, z equals 0, to z equals x plus y plus 5, but we have to have that in terms of r and theta. So that's going to be r cosine of theta plus y, which is r sine of theta, plus 5. That entire portion here is the upper bound to that third inner integral. Next problem, 15.7, number 22. This time we have a cylinder inside a sphere, and we have to find the volume of that solid. So here's a sphere. Inside the sphere, we're going to have a cone. Inside the sphere, we're going to have a cylinder. And that is probably as bad of a drawing that I could possibly make. So at this upper end here, here's the cylinder. The upper end of the cylinder is going to have a little bit of a cap from the sphere. And that's also going to be true down here. Here's the cylinder, but a little bit of cap created from the sphere. And we want to find this entire volume. This looks like maybe like a pill or something. So now if I project this onto the Cartesian plane, I'm just going to draw that little ring there, because when I project this onto the Cartesian plane, that's what I get, that ring. And so all the action goes inside the ring, goes inside that pill. So up towards you is a sphere cap. Into the computer, down deep into the computer, is a opposite sphere cap. And we're going to treat this volume accordingly. So our f function is still 1. We're still going to need the Jacobian r. Of course, I needed my transformation, which I'll just pen real quick here. Okay, we have that. We'll go dz, dr, d theta. Theta is going to go from 0 to 2 pi. R is going to go from 0 to 1. And then z is going to go from back down here, this little cap here, up until this cap here. So the lower cap is going to be z equals, let me just write that, z equals, and I would have to solve this function here for z, where I get plus or minus radical, and this is going to be the negative of that radical, minus 4 minus, and if I convert into r and theta, it's 4 minus r squared. At the upper end, it's going to be z equals the positive radical 4 minus r squared. This problem here is the final cylindrical transformation before we move on to spherical transformation. And the directions wanted us to make the transformation in order to evaluate the integral. So our biggest task here is to figure out what the space is. So let's look at the Cartesian plane. So this here tells me that x is fixed from -3 to 3. So 1, 2, 3, 1, 2, 3. And then the y goes from 0 to the square root. So that's a semicircle. And so that's going to go like this with a radius of 3. Okay, terrible drawing. And then finally, the z, which we won't be able to visualize here, but the z is going to go from 0 to a paraboloid facing down. So that's going to be flat here, flat against the Cartesian, and then when it moves up, it eventually touches the paraboloid. So our integration is going to be from 0 to pi. R is going to go from 0 to 3. Z is going to go from 0 to 9 minus r squared. Goodness, and I forgot the transformation again. And I do want you to write the transformation, even though it's a bit of a pain. Absolute value of the Jacobian equals r. Okay, so the integrand is going to be the square root of r squared, which is just r. That's nice. And then the Jacobian, so that's separate. And then dz, dr, d theta. Okay, now we're going to move on to spherical coordinates. And here in section 15.8, number 20, we have two concentric spheres that make up a solid, and obviously not full spheres. It's kind of like a jawbreaker. Anyway, in this first problem, we're going to set up the triple integral to find the volume. The problem states something a little differently, but I'm going to just say that f of x, y, z is equal to 1, just so that we get the idea here of spherical coordinates. Okay, for convention, I would like the order here to go d rho, d theta, d phi. So let's get used to that. So we're going to fix in that order. So phi, if you remember, phi is going to go from upper z and then it falls down towards the Cartesian plane. In that case, phi is going to go from phi is 0. This z axis alone is phi equals 0. And then it goes down to phi equals pi over 2. We have to be a little bit careful with the theta here, because the theta, if we actually look at it as a projection, theta is going to go from pi over 2 to 2 pi. And then rho, the respective radii of the spheres, is going to go from rho equals 1 to rho equals 2. And since we're looking at volume, we have this is 1, but we do need the absolute value of the Jacobian, which is equal to that. So there we go. This particular triple integral would give us the volume of the solid illustrated in example number 20 from 15.8. Okay, next example, 15.8, number 22. We're going to do a spherical transformation, which I have the transformation written here already for our convenience. And we'll need 3 integrals. The hardest part about this one, I think, is the integrand. And it's not hard, it's just really annoying to write. So I'm going to write the integrand as 9 minus rho cosine of theta sine of phi. That gets squared minus y, which is rho sine of theta sine phi, and that also gets squared. And we're going to close that off, so that gets closed with this to make the integrand. And then we have the Jacobian, rho squared sine phi, and we'll go d rho d theta d phi. Okay, so let's analyze this a bit. H is the solid hemisphere, so it's less than or equal to 9 hemispheres. Z is greater than 0, so we might think of that as the northern hemisphere sphere. Okay, so let's set up. The phi is going to go from 0 to pi over 2. Yes, because that'll bring us to the Cartesian plane. And then we go 0 to 2 pi in theta. And then rho is going to go from 0 out to that sphere with radius 3. And there we have it. Okay, so now for number 24. Okay, I have my transformation written. I have my 3 integrals written. I'm ready to go. So the integrand is going to be e to the square root of x squared plus y squared plus z squared. And that's going to be the square root of rho squared, so that ends up just being a rho, so e to the rho. Then I have my Jacobian, which is rho squared sine phi. That'll go d rho d theta d phi. And what are we? The first octant of that sphere. So first octant, that's fine. We're going to go from 0 to pi over 2. And then 0 to pi over 2 in theta, and then 0 to 3 in rho. Let's take a look at 26. This time, the region bounded is between the sphere. Rho equals 2. That means a sphere whose radius is always 2 and a sphere whose radius is always 4. And then they kind of give us the cone in terms of phi. So imagine phi drops down to pi over 3 and then rotates around. So phi is pi over 3 for all theta, and then we have that cone. Okay, again, the most annoying part is the integrand. Maybe I'll just start with that, the integrand. Oh, x rho cosine theta sine phi times y rho sine theta sine phi. Z rho cosine phi. Okay, now we have the Jacobian, rho squared sine phi, d rho d theta d phi. Now phi, because it is the cone, so here's the cone, where phi, remember phi is 0 to phi, the angle being pi over 3. That one's pretty straightforward. That's going to be from 0 to pi over 3. And then theta, well, that's just going to do a full revolution, 0 to 2 pi. And then rho is going to go from rho equals 1 to rho equals 2 to rho equals 4. So imagine cut out a sphere bottom to this and then sphere top. Oh, what does that look like? Oh, it kind of looks like this, except it wraps all the way around, something of that nature. I find the next problem, number 30, to be very interesting. So we have a cone inside a sphere, or a cone and a sphere. So there's the cone cross-section. Here is the sphere's cross-section. This question, what does it want? Let's see. Find the volume within the sphere, okay, but below the cone. Now, when you see the words below the cone, that means in the negative z direction. So that's all of this. Remember, this is a cross-section. So, gosh, if you had a sphere and you drilled a triangular cone shape out of it, you would get this resultant solid. And I'm just looking at a cross-section of it. The most tricky part about this is finding phi because it's not explicitly given. So here's phi equals 0, and we need to find this phi in order to set up our integration. It'll go from whatever that phi is down to pi over 2. Now, there are several ways to do this. I'm going to give you just one of many ways to do this. And I'm looking at the cross-section again. And There's a triangle, and that cross section kind of goes up like this. But if I look at this triangle, oh goodness, that triangle is this triangle right here. In order for me to try to find phi. And I'm just going to redraw it because I got a little bit ugly. Here's phi. Well, the one thing I know for sure that this is 2. I know that this is 2 because the radius of this sphere is 2. So that is 2, I know for sure. Suppose now that I wanted to find this value here, or this value of the triangle, which is this value here. So what's going to happen for this particular distance or z value, that's going to be the same z value for both the cone and the sphere. So I would basically be wanting to find for what z value do those two intersect. And if I take the equation of the sphere, x squared plus y squared plus z squared equals 4, and I solve that in a system with the cone, which is z squared equals x squared plus y squared, if I put those two together, then I get x squared plus y squared, and then the z squared was also x squared plus y squared. That would then equal so we have the equation of the sphere, x squared plus y squared plus z squared equals 4. But if we solve that in a system with this green circled cone, then I see from the cone that z squared equals x squared plus y squared. So the x squared plus y squared becomes z squared and z squared here. And so now we have 2z squared equals 4, and z comes out to be plus or minus, but we're looking for the positive distance. Z comes out to be radical 2. And we could also find then quickly Pythagorean theorem that this is radical 2. All right, and based off all of that business, the tangent of phi is going to be 1, and so phi has to come out to be pi over 4. Please note that I do recognize that you could have figured that out on your own, and it's okay, but I'm giving you just one strategy to find that phi is pi over 4 when the two curves intersect. And so now for our integration, phi, again here, phi went from pi over 4 to phi equals pi over 2. So pi over 4 to pi over 2. This is going to make a full theta revolution. And then we're going to go from 0 to 2. This is just volume. So 1, the Jacobian d rho d theta d phi.